So what is this class about? Well, this class is about the hardware-software interface. But to understand that, first let's see what's hardware. Well, hardware is a part of your computer made of atoms. It's the physical part of your computing device. Okay? And software is this thing made of bits, which is the program that runs on top of your hardware. Okay? But for that to happen effectively, there are many, many layers of abstractions between the hardware and the software. Okay? And this is what we call the hardware-software interface. And the reason we want you to understand what a hardware-software interface is that it's going to help you understand better how computers work. It's going to make you a more effective programmer. It's going to make you better at writing efficient code. And it's just going to make you a better computer science scientist. So let's look at these three pieces of code here. So here we have a simple statement that does a conditional and performs an assignment here. And this is written in a language like C or Java. Okay? Now this piece of code here is also it's also a program, and this is written in what we call the assembly language. Okay? The assembly language is just a much lower level language that's pretty close to hardware, and it just happens to be a abstraction, a simpler way of looking at machine code. Okay, so the machine code is just a sequence of zeros and ones. Processors only understand zeros and ones. It interprets them in different ways. Now, so what's in common between these three pieces of code? Well, all of them do exactly the same thing. They're equivalent. But you'd rather write in this language here, because it's much easier, it's much more natural for humans to write. Okay? So it's much more human friendly. But as I said before, the hardware likes bit strings. So zeros and ones. So a digital computer likes zeros and ones because it's very easy to represent with electronic circuits, because zeros is a low voltage and one can be represented as a high voltage. Okay? So and the machine instruction is actually much shorter than the number of bits we would need to represent the characters in the assembly language. It's a much more dense encoding of the assembly language, the assembly instructions that we see here. Okay, but there's a very direct correspondence between these simple assembly instructions and some of the bits in machine code. Now, let's look at the hardware-software interface from a historical perspective. So at first, the hardware-software interface was very, very simple because hardware was simple. Hardware was very, very primitive when computers started. Okay? So humans were able to write code directly to hardware without any abstraction at all. But then people got and that means that software was also very primitive, because the software primitives reflected the hardware pretty closely. But then people got really excited about computers, and it's like, hey, computers can do all of these things, so they ended up writing more and more complex pieces of code. That meant that humans could no longer, keep up with the complexity of writing machine code directly. So the assembly language was invented. The assembly language, as I said before, it's a very, very simple computer programming language that's pretty close to what the hardware can do in terms of its primitives. And one assembly instruction translates to one machine instruction. Okay? So, but the big difference is that the assembly language is much easier for humans to read, because they have, first of all, they have character strings as opposed to just bits. Okay, so humans can understand much, much easier, so it's much easier to read and write. And it can also use symbolic names for values. Okay, they can use things like register names, variables A, B, and so on. Okay, so now there's a piece of code here called assembler that takes a program written in assembly and generates zeros and ones machine code, which is what the hardware likes. But even then, that wasn't enough, because programs were getting more and more complex, so we needed yet another level of abstraction that's much higher level. Okay, so these are things. So these are languages, abstractions, languages like C and Java. They're much, much higher level, and you can write statements like A equals B plus C, for example. Okay, and one statement in this high-level language can translate to many, many assembly language instructions. Okay, so but now we need yet another component in our path from the user to the hardware here, which is the C compiler. The C compiler takes C code and generates assembly code. Remember that this is assembly. Okay? So, and that's much higher level. That means humans are much more productive at writing code for that. So now, let's look at the entire lifetime of a computer program. Okay? A computer program has three basic steps in its lifetime. There's coding time, which is the time that the human spent writing the program in a high-level language like C. Compile time is the time it takes to get your C program and generates machine code executed by the hardware. Okay? And when the hardware is executing the code, we call that runtime. Okay? So now compile time is something that happens just once, and if you execute your program many times, that means that it can amortize the cost of compilation a lot, right? Because if you spend some time compiling the program, you're going to execute so many times. It doesn't matter if you spend a little bit more time doing compilation. Okay? And in fact, during this process here, during the compilation process, the compiler can spend a little bit more time generating the code in order to do optimizations that are going to make your program faster without having the programmer improve the code itself. Although if you do want to generate really fast code, you do want to regenerate. You do want to start with good algorithms first. Okay? So a big theme in this class then is the hardware-software interface. Okay, so that includes how the hardware, in other words, zeros and ones and process executing instructions, relate to software. In other words, for example, your Java program. And the other part of this theme is that computing is about abstractions. Computer systems are complex. In order for humans to understand and design effective computer systems, we need abstractions. Okay, so computing is a lot about abstractions. But we can't really forget reality. Well, the goal of an abstraction is to abstract reality and make it simpler to think about. But we don't want to completely ignore reality because that leads to inefficiencies, leads to other problems. Okay? So we're also going to talk about what are the abstractions that we use and what do you need to know about them. Okay? So, well, you know when they break down and you have to peek under the hood. You also want to know because it will help, we will know about the abstraction because it helps you understand what kind of bugs can they cause and how you find them and so on. But knowing the hardware-software interface ultimately is going to make you better programmers. It's going to help you begin to understand important concepts that have evolved in building ever more complex computer systems.